Hi, everyone. My name is Chérif Matta. I am a professor at Mount St. Vincent University here in Halifax, Canada, and I am the host of this program, Conversation with a Scientist. And today it's my great pleasure to interview or discuss, to talk to Professor Lou Massa, who is professor of chemistry and physics at Hunter College in the City University of New York, and a senior visiting scientist at the Naval Research Laboratory at the United States in Washington, D.C., about a topic called quantum crystallography. And Dr. Massa obtained his bachelor degree in physics from Le Moyne College. He then followed with a master's in science in physics from Clarkson University and a PhD from Georgetown University, also in physics. He then followed that by a postdoctoral training at Brookhaven National Laboratory before becoming a professor at Hunter College in City University of New York. Professor Massa's research primarily focuses on the electronic structure of biological molecules and the development of a field called quantum crystallography, which integrates structural crystallographic information with a quantum mechanical theory to extract more from the experiment that is commonly assumed. Professor Matta received a number of distinctions for his work, including the ACS Westchester Distinguished Scientist Award, a Distinguished Visiting Professor title at the U.S. Naval Research Laboratory in Washington, D.C., and an honorary doctorate of humane letters from this very university here, MSVU, along the likes, previous laureates of this honorary doctorate include people like former United States Secretary of State and Senator and former First Lady Hillary Rodham Clinton and Nobel Prize winner Ada Yonath. So he's in a good company. And he's currently a member of, and formerly a consultant of the Commission on Quantum Crystallography, a name, by the way, that he coined, of the International Union of Crystallography. I'll just say a little bit about his distinctions, very briefly, because otherwise we're going to take the whole program. He's an author of nearly 250 scientific publications. He's a host of a very well-quoted TV series in New York by the name of Science and the Written Word. And he's a co-author of two books, including the one that we are going to discuss mainly today, this book here on quantum crystallography, and another book that stems out of his program, which is Science and the Written Word. We are going to also touch about this book near the end of this program. He secured funding from many agencies, including the National Science Foundation, the NSF, the National Institute of Health, the NIH, IBM, NASA, U.S. Naval Research Laboratory, to name a few. He has held visiting professorships at Harvard University, Brookhaven National Laboratory, U.S. Naval Research Laboratory, Université de Bordeaux in France, University of London, and several others distinguished places. He has been an editorial board member of Structural Chemistry, a journal in chemistry, and Science and Technology editor of the City University of New York. He has been guest editor of several special issues. We're going to discuss some of them. And he has given prestigious invited lectures at Princeton, at Harvard, at Northwestern University's Brookhaven National Laboratory, the U.S. Naval Research Laboratory, University of London, the Weizmann Institute of Science, Uppsala University, Peking University, and many others. So without further ado, Lou, would you be able to tell us a little bit less formally about yourself? Where do you come from originally, both geographically and intellectually, and where are you now, and how did you end up here?
Yeah, Chérif. Mm-hmm. Well, thank you very much for inviting me here, and of course, thank you for the generous introduction. I'm very glad to be here. So you're asking about where I come from. So I'm from an Italian family in upstate New York. And as you indicated, I went to Le Moyne College in the town that I grew up in, actually, near Syracuse, New York. And That's where I learned physics, and I pursued physics thereafter, as you indicated, at Clarkson University on the border of Canada, way up in upstate New York, and then subsequently at Georgetown. So that was my career path getting started in the field of physics.
I think once you mentioned that you mentioned to me, because we're friends as well, right? And you're my mentor in a way.
Yes.
So once you mentioned that initially you had an interest to study philosophy, and then somehow you ended up in physics. So what's the story there?
Well, the basic story is I'm a Jesuit product. You know, I went to Lemoyne College, a great Jesuit school, and one of the requirements there is 4 years of theology and philosophy. So I was enamored of discussions in philosophy and so on. And I actually had been accepted to a PhD program in philosophy. But at the very last minute before going to school, I told the head of the physics department at Lemoyne College that I had this insight.
Revelation.
I had this revelation that physics was a much more important, it would have more societal impact. And I decided to change my mind, and that's how I went to Clarkson University.
But from the discussion with you over the year, you maintain a very strong interest in the philosophy of science and philosophy in general.
Yeah, of course. Yeah.
Yeah. So
I actually wrote a rather elaborate couple of chapters in a philosophy book about Descartes, and the chapters had to do with the influence that Descartes has had on mathematics and physics. But it was a philosophy book.
Right, right. I am very interested in philosophy as well, as you know. So, Lou, the center of our discussion today is the book that you have published recently that I showed the audience before this one about quantum crystallography. So it's kind of an interesting set of words, quantum and crystallography. So can you explain each one separately and why they are combined here in the title of this book?
Yes. This is a book co-authored with my former student, Lulu Huang, and with Chérif Matta, in fact. Yes, quantum crystallography. So science has equations of motion, and in terms of microscopic science, the equations of motion are the Schrödinger equation. And quantum mechanics is all about solving the Schrödinger equation for that wave function solution. That's quantum mechanics. It's a probability theory. The physical interpretation of that wave function is it delivers the probability for where the electrons are in a physical system. So that's the notion of what is quantum mechanics. It's all about solving the Schrödinger equation for the problem of interest. But then there's crystallography. Crystallography is a structural science.
And it has nothing to do with the crystals that bring you luck and stuff. This is a solid science, right?
Yeah.
It's actually one of the most important techniques in scientific research, to discover drugs and discover materials of importance and materials to use in the space shuttle, etc., right?
Exactly.
Yeah.
Structure is fundamental. To know structure is to know function. Once you know the geometry of something, you are on your way to knowing how that molecule reacts with other molecules, why it's important, how it behaves. So crystallography is about the problem, what is the atomic structure, which boils down to the question, given a molecule that's made of atoms, what are the Cartesian coordinates of every single atom in that molecule? And the answer to that question is delivered by the X-ray scattering experiment of crystallography. So that's a discussion of what is quantum mechanics on the one hand, and what is crystallography on the other hand. Then we come to the topic we're focused on, which is quantum crystallography, and that's the problem of how to use the equations of motion to in fact describe the electronic structure that's associated with the atomic structure of classical crystallography.
Okay, I guess at this point we should get to your slides that you have very kindly provided, and maybe we can describe the slides a little bit. So the first slide here we have is this one. So can you tell us a little bit about these slides, and I will move to the next,
So the story of my efforts in quantum crystallography begin with my work at Georgetown University with my professor, Bill Clinton.
Nothing to do with Bill Clinton, the president.
Well, as a matter of fact, Bill Clinton, the president, was a student at, which you may not know, was a student at Georgetown University at the same time that I was there as a graduate student.
Have you bumped into him? Do you know him?
No, I did not bump into him. But he actually ran for office to be the president of the student body at Georgetown University.
Bill Clinton, the former president.
Bill Clinton, the president,
yeah.
In any event, Bill Clinton is the famous professor of chemistry and physics, and we were interested in the problem in quantum mechanics of what is the density matrix. So in the bottom of this slide, in the lower left-hand corner, there is the definition of the density matrix. It's symbolized as rho sub 1. And you'll notice it's a function of the coordinates of electron position, r and r prime. And the definition is given the solutions to the Schrödinger equation, symbolized by the Greek letter psi. If you take the square of that wave function, that probability term, which depends on the coordinates of all the particles, if you integrate, if you average over the positions of all the particles, where they are and what their spins are, if you average over all of that, except for the coordinates of one particle called r, that defines mathematically the one-body density matrix. And that was the object of our great interest, the density matrix. But as regards crystallography, the object of crystallography is the density. And that's symbolized by the Greek letter rho of r. It's related to the density matrix because it's the diagonal elements of the density matrix. In other words, it's part of the density matrix. The density matrix is the more general object, and it was for that reason that we are more particularly interested in the density matrix.
And so let's move to the next slide. So briefly, and for the in as little technical language as possible, what that N representability here means for someone who'd never seen that before.
So N representability is jargon, more or less, in the field of chemistry and physics, which has the following meaning. It has the meaning of a connection between the density matrix and the wave function from which it is derived. So in the previous slide, I showed that if you know the wave function, by averaging over all of the particle positions, you can deliver the density matrix. But N representability is associated with the opposite question, that is, given an arbitrary function of the coordinates of one particle, does that in fact come from some possible wave function?
So basically, in very simple words, what would N representability be?
N representability is a mathematical criterion which ensures that an arbitrary function of one position, in fact, comes from a complicated wave function that is a solution to the Schrödinger equation, the fundamental equations of motion. So N representability is the guarantee that those arrows that you see on the slide go in both directions. Starting with the wave function, that delivers the density matrix, and vice versa. The arrow goes the other way, that if you have an arbitrary density matrix, in fact, it's validly related to a wave function.
And this is the constraint that you impose in order to deliver the density matrix, in addition to constraining it to reproduce the experimentally observed so-called structure factors, right?
Exactly right. Yeah. That's our basic contribution. It's the idea that N representability is fundamental to that density matrix which represents the X-ray scattering in the crystallography experiment.
Perfect. Thank you very much. So let's move to the next one. So this is a summary, basically, of everything we have been saying. It's in picture form, the idea that X-rays, which shine on some complicated arrangement of atoms, whose basic equation is the Schrödinger equation in the upper right-hand corner, when you put those two together with the scattering that's pictured, that delivers the ultimate density matrix at the bottom of the slide. And that density matrix is guaranteed to be N-representable and to satisfy the X-ray scattering experiment as well. So basically, you are satisfying both or you're extracting information from both the experiment, but constraining it to produce a result or a measurement that is consistent also with the foundational physical theory, which is quantum mechanics, right?
That's, well said.
Yeah.
Yeah. It's the theory and the experiment together.
Yeah. So how about this slide? This is the early work that you started this field from, right?
This is one of the first papers with Bill Clinton, which prove that the Clinton equations will do both things. It'll deliver the quantum mechanically valid density matrix and at the same time satisfy the X-ray scattering factors. It's the proof that you can extract from the X-ray data the quantum mechanics of the problem.
So how about this one?
That
in 1972.
Yeah.
Now we're 72.
Yeah.
Yeah.
1972. It's the proof that the N representability can be imposed by requiring that the density matrix be a projector. So that's mathematical jargon, which means that if the density matrix is multiplied by itself, it gives itself back. P squared is equal to P is the way it's written mathematically. And with such a density matrix, that delivers the antisymmetric wave function, the single determinant approximation to the solution of the equations of motion.
Okay. And this is 1972. I think it's organized by chronologically. So next we have this picture, which is, I assume, your time in Brookhaven National Laboratory.
Right. So I had an appointment after Georgetown at the Brookhaven National Laboratory. And you can see that this is the basis of the accelerator, which delivers the X-rays, which allow you to determine X-ray structure.
So it's a synchrotron?
It's a synchrotron. And I spent 3 years there, and it was a very important center of crystallography. So I learned a lot about crystallography while I was there.
And you met a lot of people there, which are coming in the next slide, I guess, right?
Yeah, I could mention a few of the important people that I interacted with. But Brookhaven was filled with crystallographers. But for the sake of time, I'll just mention, for example, Walter Hamilton, who was a student of Linus Pauling. He was considered to be a genius. People used that word about him. His peers talked about him that way. He's the inventor of the protein data bank, which is of tremendous importance. And he was one of the important backers of the idea that we could, in fact, extract quantum mechanics from the X-ray scattering experiment. Philip Coppens, who's tremendously important in the field of crystallography and what has come to be called quantum crystallography, he was present during my time at Brookhaven. And importantly, during that time, he showed by measurements with the high flux beam reactor, a neutron source, and with X-rays, he showed that you could measure the non-spherical aspects of the electron density.
And this is the picture we have on the left here.
And that's right next to his image. And that shows, that's the heart of quantum crystallography, essentially. It shows that there's experimental information that is non-spherical and which is amenable to measurements. And Coppens, I think, was at the forefront of showing that. This is a picture. The man in the white sweater is Ivan Bernal. He was a giant in crystallography. I still talk to him once a week. When I was at Brookhaven, he did an experiment that showed that the high flux beam reactor neutrons could be used to solve crystal structures using the mathematics of direct methods that Jerome, Karle, and Hauptmann had invented and so forth. So he's a very important crystallographer to this day.
How about this picture? Now we are IBM Watson Research Center in Yorktown Heights.
Yeah. So those people that I mentioned just previously and several of my other colleagues, we all left Brookhaven around the same time. And Sam LaPlaca, who was a close collaborator of Walter Hamilton, went to Yorktown. He was the in-house crystallographer and expert in crystallography. And he was a friend of mine from Brookhaven days. He invited me to spend a year on sabbatical there. So I spent a year in that cylindrical building there. And
that's an accelerator as well, or what?
No. That's just an architectural technique. But it's situated beautifully on a hilltop in Yorktown. And so what we did there was we used what was at the time the most accurate diffraction data available due to Larson and Hansen. And there's a picture of the beryllium crystal. And we applied the projector formalism, the quantum crystallography formalism that we had invented and discussed together at Brookhaven. And we proved with this crystal that you could extract the quantum mechanics from the X-ray scattering data. And something that I don't want to discuss because it takes time, but I'll just mention that Bader and Rudenberg had talked back and forth.
Richard Bader and Klaus Rudenberg, right? Two very noted quantum chemists.
Both famous, important people. They had discussed back and forth what happens to the electron density upon bonding. And Rudenberg argued forcefully that the kinetic energy is reduced upon bonding, and the beryllium...
The kinetic energy of the electrons.
The kinetic energy of the electrons in that molecule, that'll be reduced upon bonding. And we proved with this accurate beryllium quantum crystallography that Rudenberg's point was well taken.
Information that could never have been
It could not have been extracted with classical crystallography, right?
You only get the electron density with the classical crystallography, but not all the information about the energies and their components.
You cannot calculate the kinetic energy, which was the Rudenberg object. You can't calculate that with the density alone.
Yeah.
But in our experiment, we got the density matrix, which allows exactly that calculation.
Right. So then we moved to, we were leaping in time here, decades. And now you are at NRL, the Naval Research Laboratory. I guess you went there...
1985, I would say.
Yeah. Right.
Yeah, I met Jerome, Karle, Jerome and Isabella at a meeting in Philadelphia, and we got on famously, and I began working with him for the next 30 years.
So you were going there every summer, spending like 3 or 4 months there.
All summer long, every summer for over 30 years.
Yeah.
And during that time, Jerome was awarded the Nobel Prize, Jerome and Hauptmann and Jerome, Karle, for what has come to be called the direct methods of crystallography.
Right.
What it boils down to is it's the mathematics which, if followed, given the X-ray scattering data, will deliver the XYZ coordinates of every atom in the crystal. It's the answer to the classical crystallography question: where are the atoms in the crystal? That's the Nobel Prize.
And here is Isabella Karle with another Bill Clinton.
Here is
and
Isabella.
Al Gore.
Yes.
Yeah.
Here's Isabella Karle, the wife of Jerome and a lifelong collaborator.
You published several papers. You and Isabella and Jerome published several papers together.
Yeah.
And you wrote a chapter on her in I think it was like after her passing, or
No.
Or during her.
It was during her lifetime, actually.
Yeah.
The American Chemical Society asked me to write a paper responding to the question, how is it possible that Isabella did not win a Nobel Prize? Because it was her experimental work that made it clear that the mathematics of Hauptmann and Karle would in fact deliver the crystal structures. She's the one who actually used the mathematics. She's the one that did the experiments that delivered the crystal structures. And she should have shared in the Nobel Prize. And I wrote a paper for the American Chemical Society indicating exactly that fact.
And she was awarded the Aminov Prize, which is awarded by the same committee of the
Nobel Committee.
The Nobel Committee, yeah, right.
Yeah. Very importantly, she won this this is basically the highest prize that you can get within the United States.
Yeah.
It's called the National Medal of Science. And you can see from this slide that it was awarded by the heads of the state. And something that people find amusing is a story I once told to the effect that Bill Clinton tried to get a hold of me, and I wasn't in my office, and he asked
You were in your office in New York, in Hunter College.
I was at Hunter College.
And then you receive a phone call.
I received a phone call, but I was not in my office to answer. So Bill Clinton then called the secretary of the department and said, would you track down Lou Massa? I want to talk to him. And so the secretaries actually did find me in another laboratory, and they were totally excited and said, Lou, Bill Clinton is on the phone.
From Washington, D.C.
Calling from Washington, and he wants you on the phone immediately.
Okay.
So in any event, it turned out it was Bill Clinton, Professor Bill Clinton of Georgetown, that was trying to get a hold of me, and it was not the head of state.
Yeah. Okay. So now we jump to 95. That's a big jump. So now you publish, this is the first time a paper is titled with the phrase quantum crystallography, these two words fused in one phrase. And I understand that this paper wasn't easy to publish. Could you tell us something? And what is this paper about? What's new in this paper in 95? Why it was difficult to publish?
So what's new in the paper is we were talking about the use of what came to be called the kernel energy method, which is an interesting idea. At the Naval Research Lab, we changed our focus from small molecules to big molecules. And it turns out, we found, that you could take a big molecule, no matter how big, and just mathematically chop it into small pieces. Mm-hmm. And therefore, you can calculate the small pieces.
These ones.
For example, if you look at the slides on the stick figure on the left of some larger molecule, notice how you can break it up into its smaller pieces. And then if you...
Color coded here, like the blue piece is the blue, the green, the black piece is black, right?
Exactly. Yeah. The little black pieces in the column on the right. If you take those, you can put them back together according to a kernel energy method formula that we discovered. But notice that every one of the pieces could be sent to an individual processor, and therefore you speed up the calculation amazingly if you're doing it all in parallel.
Let alone that the quantum calculations speed up considerably when they are on smaller molecules. You know, it's a power law. So
exactly right. And to get back to that paper, the word quantum crystallography is in the title of the paper. So the science of the paper was fine and received no objections from anyone. But the referees were upset about the fact that we would call this work quantum crystallography. And we simply told the referees they could accept it or reject it, but they could not write the paper for us. And that, in fact, in as much as we were injecting quantum mechanics into the description of the crystallography, we felt totally justified in calling it what it was. Quantum crystallography.
And for the general public, the reason you break up a molecule like this is not, this is a small example, but in reality you are trying to break up large biological molecules in order to be able to compute their properties fast, which is impossible at the moment due to their size. That's the reason you're doing this, right?
Exactly right. Yeah. We're talking about not only molecules, but systems of molecules that might have hundreds of thousands or even millions of atoms.
Which are inaccessible for quantum calculation by normal methods. So this is the innovation here. And the reason you do this is in order to calculate properties that could be used in drug design, in material design.
Exactly
that kind of thing, right? Yeah. I'm trying to just make it clear for the general audience here why we're doing things. And how about this? I mean, this is from the website, the Nobel Prize, the Nobel Foundation website, and there is an addendum which actually mentions your name and your former student, Lulu Wang, by name. What is the story here? What is this?
Well, Jerome, as a Nobel Prize winner, was asked to update his biography, and he was kind enough to say in that update that he was working with Lulu Huang and myself, and that we were making an important contribution to his work. And he was thinking particularly about the kernel energy method that you and I had just discussed a bit.
So that was quite an interesting and impressive tribute.
Well, because of the importance of Jerome, absolutely.
And now we're jumping to 2017, and then we have this special issue of the Journal of Structural Chemistry, whose editor-in-chief is a very distinguished scientist, István Hargitay in Hungary, very important scientist, who is the chief editor of this journal. And he invited me to edit a special issue in your honor. In 2017, and the issue is titled A Path Through Quantum Crystallography. This is the title of the issue, and it is a very thick issue with some 80-something authors contributing. Could you tell us something about this issue?
Well, first of all, it was very kind of István Hargitay, this important scientist, to invite you to edit that journal. And in my honor, and I definitely was honored by the existence of having something like 80 people from all over the world contribute papers. That would have included the Nobel Laureate Yonath, for example. And I also wrote an article called My Own Zigzag Path Through This.
Why zigzag?
Well, because as you know, science is not straightforward usually. It's a zigzag process where you make some progress and you're thrown backwards and you
have faux pas, you have
exactly.
you go backward.
Yeah, you go back and forth. And you literally zigzag through the world in a sense in terms of the people you meet and who you work with. And
there is chance opportunities. There are things that are by design. There are, right?
Yeah,
yeah.
all of that, exactly right. So I wrote that article.
It's kind of an autobiography, right?
It is. It's sort of an autobiography of the experience that I personally had in going through quantum crystallography from beginning to something like present day times.
With all the people you met, etc.
With all the people I've met and so forth, yeah.
Now, in the same issue, this thick issue of structural chemistry, the Nobel Laureate of 2029, Professor Yonath, contributed this work, which I understand that you collaborated with her on several papers about the topic of this, which is the ribosome, right? Can you tell us a little bit about your work on the...
Yeah, when I was at a conference at the Weizmann Institute in Israel in 1977, apparently, I think that was the year, I met Yonath, and she told me at that time about solving the structure of the ribosome, which was a totally amazing thing. And of course, that's why she's a Nobel Prize winner. She solved the structure of the ribosome. So
she shared the Nobel Prize with Stites and Ramakrishnan, right?
Yes.
Yeah.
Yes, that's correct.
Mm-hmm.
Subsequently, Jerome, Karle, and I talked to her about the quantum mechanics of formation of the peptide bond by the ribosome. And she collaborated with us and her students and our students and so on. And we wrote a paper about how it is that the peptide bond puts the bond together.
What for the general public, why is the peptide bond so important? What is a peptide bond?
A protein is a sequence of amino acids, and the amino acids have to be hooked together, and that hook, in fact, is the peptide bond. So this ribosome is this gigantic machine that takes pieces called amino acids and snaps them together
together to form the proteins.
Very rapid time and sends that protein out of...
And of course, most of our bodies are protein, and most of the enzyme that accelerate all the biological reactions in our bodies are protein, and hence the fundamental importance of the ribosomal catalysis of peptide bond formation, right?
Exactly right.
And you've discovered the transition state of this reaction.
And we discovered the transition state, yeah.
And you worked on another project on this, like evolutionary...
Well, Yonath and her group had a remarkable idea, which was the present-day ribosome, which is gigantic, has at its core what is perhaps the precursor of the modern ribosome. It would be like an evolutionary precursor. And if you pluck that precursor out of the present-day ribosome, the question arises, could it function as a molecule that would hold together the pieces required to form the peptide bond? And to get back to previous discussion, Lulu Huang used the kernel energy method to show, in fact, that with a precursor that had maybe 10,000 atoms in it, a large number, but not millions of atoms as occur in the full ribosome, she showed that, in fact, it could function. You know, so it was quite interesting.
Very interesting indeed. So moving on to 2018, and so what are we looking at now here, Lou?
What we have here is a pair of issues in the Journal of Computational Chemistry that have been edited by Matta and Massa that deal with the topic of quantum crystallography, and they were important enough that they became cover issues.
And how about this one? Now we are 2019 and 2022.
Well, similarly, Matta and Massa published articles again in the International Journal of Quantum Chemistry, a journal that was founded by the famous theoretician Per-Olof Lövdén, the Swede. And you and I published these two articles that are, again, cover issues.
And that brings us to 2023.
So this is a recent book. It's about a year old.
This is, again, I will show it again to the audience, this one that
we
started the program.
Quantum Crystallography, co-authored by Matta, Huang, and Massa. And the pictures along the right-hand side of the slide indicate Lulu Huang, a co-author, and Yonath, the Nobel Laureate, that wrote a preface to the book. The bottom right corner is a picture of a very well-known philosopher of science, Olympia Lombardi, who was kind enough to write a really remarkable sort of concluding assessment of the importance of our book in an epilogue at the very end of the book.
She puts it in context. She put the quantum crystallography in a historical context of sorts.
Exactly right. We're very grateful for that.
Yeah, we're grateful indeed to Olympia. And the book has been reviewed by, again, the very prominent scientist, Professor East van Hargitay. Can you tell us something about this book review?
Well, the main thing to know about this book review is it's of a very scholarly nature. I mean, he really delves into the meaning of quantum crystallography and has his own examples of why this is important and so on. I was really amazed at how scholarly this was. You don't always see that in a book review. Something I could tell you about Istvan is the way I know him is he's important in neutron scattering. And Jerome Karle and Isabella Karle were not X-ray people at the outset. They were neutron people. And of course, they knew each other through neutron scattering. And Hargitay's family and the Karle family were very close friends. And of course, in as much as my family was very close to the Karles for well over 30 years, naturally I got to know Istvan as well. And I'm totally grateful that he was interested enough in this book to write this scholarly review that we're looking at right now.
And I think you invited him in your program, right? In your
I've also interviewed him
TV program
in Science and the Written Word. He wrote a book about symmetry, and we had a tremendous conversation about symmetry.
I think he edited and wrote something like 50 books, 50, which is he's a tremendous scholar. And what about this picture?
This picture is important because it codifies the fact that there was a very important, small but important meeting in 2017, as I recall, in Nancy, France. And the meeting was basically called for the purpose of discussing what is the nature of quantum crystallography and where is it going? Is it important or not, and what's going to become of it? And there were these 20 people from all over, mainly the Western world, the United States, North America, South America, and it lasted for 2 or 3 days and gave rise to a paper that was co-authored by all the people in that picture. Their names are listed at the bottom.
And this picture is actually from the paper.
This picture is from the paper. And if one wants to quickly get a sense of what is quantum crystallography and where is it going, all of these people have their own niche in the field, which is not necessarily closely related to mine. It can be quite far afield from my interests. But if one of your viewers wants to quickly get an idea about quantum crystallography, what's its present state, and what are its possibilities, to read this paper that emanated out of Nancy in 2017, that's a good place to start.
Perfect. Thank you very much. And you have a wide interest, Lou, and you have collaborated with many people in your careers. And, one of the areas that are long-standing interest of yours is the area of astrochemistry, in the sense of the clusters that occur in empty space between the stars in our galaxy, that give rise to the so-called diffuse interstellar bands, which are absorption bands that no one knows exactly what are the molecular carriers that give rise to these bands. So, and let me back off a little bit. You've published a Nature paper in the late 70s about hydrogen clusters in space, and you've published a subsequent few articles in the 80s about that. I know for a fact that some experimentalists have actually found them decades later in the laboratory, these hydrogen clusters that you predicted, which is the dream of any computational chemist, is to predict something and then years later the experiment confirms it. So can you pick up from here the thread?
Yes, well, the diffuse interstellar bands is the oldest spectroscopy problem associated with astronomy. It's over 100 years old. Mary Leah Hager, 100 years ago, discovered these diffuse interstellar bands. And the question ever since has been, what is the chemical source of that spectra? And this is something I learned about when I was at Brookhaven, wondering about what could the chemical source be. Well, it's obviously something in outer space, in the cosmic clouds between us and the stars. And if you ask yourself what's out there, the most abundant thing in chemistry is hydrogen. That's what's out there. The universe is mainly made of more of hydrogen than anything else. Mm-hmm. So it's not the ordinary forms of hydrogen. They've all been disqualified as sources. So the question becomes, what could it be? So I invented those molecules you talked about, which are ion-induced dipole molecules based on H- attracting H2 molecules about it. Mm.
Well, they didn't prove to be the source of diffuse interstellar band, but they had been proven sufficiently stable to be observed in the lab, which is a great vindication of your work, kind of thing, right?
Yeah. Oh, yeah. And not only that, it's still not clear that they are not contributors to some aspect of the diffuse interstellar bands. But for us, the point is, it's those hydrogen ions that got us interested initially in the problem of diffuse interstellar bands.
So why are we looking at these people while
subsequently, it turned out that you and Magis and Tina Harriet and so forth became interested in the problem, and then new ideas developed as to how we might make small steps towards answering the question, what might these carriers be causing the interstellar band? So what we have here is a picture of what you might call the diffuse interstellar band party or group. Yeah. And
we call them DIBers.
Yeah, the DIB group. So Dan Magis is, of course, an important astronomer. Professor Tina Harriet is a general relativity expert. Here at this very school that we're speaking from, Circes Maria Boado from Mexico is an expert quantum chemist and an important contributor to this problem. And then there are the students along the bottom, Alice, who's a student of Circes, and she's a month or so away from getting her own PhD and has been an important contributor. The Smith family, Fraser and Emily, brother and sister, who were authors of the very first papers that we published in this field. And Eilish, more recently, a graduate here, an undergraduate.
From Mount St. Vincent
From Mount St. Vincent University. So it's a group of people who are intensely interested in the problem and who are finding their way towards suggestive possibilities as to how we might look at the whole problem.
Thank you very much, Lou. And I might interject here that we have a special program from this series, A Conversation with a Scientist, where I have chat with Tina and Eilish about that very problem, diffuse interstellar bands. So the viewers that are interested can watch that episode here on a conversation with a scientist. So finally, you might have noticed that this program here, A Conversation with a Scientist, is in part at least patterned after a program that you had at City University of New York TV back in the early 2000s. That is called Science and the Written World, which is the basis of this book that you published with Oxford University Press.
Yes.
And which is a series of interviews with very highly placed scientists, including several Nobel Laureates. If I count correctly, it's about a dozen Nobel Laureates. And here we have like 4 snapshots with some of them. So you have had an active involvement in the dissemination of science to the general public yourself. And can you tell us a little bit about your program and this book?
Well, the fundamental thing is, I think it's important for scientists such as we are to try to communicate the importance of what we're doing to the general public. And this program of mine that was generated at the City University of New York was an attempt to, in fact, do exactly that, which was to tell the general public what some of the most important scientists in the world are doing and why it's important to them. So what you've pictured here is 4 Nobel Prize winners, Watson and Dudley Hirschbach, Gertrude Elion, and Roald Hoffman, all of whom were interviewed on that program. And as you mentioned, there were more like a dozen Nobel Prize winners altogether, and maybe 50 important scientists that I interviewed.
And they are available on YouTube, most of them, not all of them, but they are in the archives of City University of New York, right?
That's right.
And I think the
Gertrude, by the way, she's a graduate of the chemistry department that I teach.
And then she had a career in Glaxo, I think, right? Or
Glaxo Wellcome, Gertrude Elion is of tremendous importance in the discovery of drugs for all sorts. I mean, I myself take drugs that Gertrude Elion has developed. She told me something which I find so fascinating, which is she never gives a talk, but that someone will come up from the audience and thank her for some reason or other related to some medicine that
she invented
that has saved the life of one of their children, etc. So definitely very interesting people.
And James Watson is, of course, of DNA
Watson
fame.
And Crick.
Watson and Crick.
Yeah.
So iconic figure. Right.
Yeah.
And so your book is essentially a transcription of the interviews, right?
That's right.
Yeah. And you've very kindly, this is the actual logo of the program, which is funded by the Dreyfus Foundation, right?
Yeah.
This is the
That's
logo.
Right.
And you have very kindly dedicated this copy for me here. Very kind of you. Thank you, Lou.
Oh yeah, you're totally welcome. Yeah.
So on that note,
Chérif, this is such fun and such pleasure talking to you. Thank you.
The pleasure is all mine, and you're welcome here in Halifax, your second city.
Thanks so much.
And we hope to see you more and more here, Lou. Thank you very much for granting us this interview.
Thanks so much.
Thank you.
Yeah.
Thank you, the audience, and I'll see you in the next episode of Conversation with a Scientist. Thank you.